after the class? Yes or no?
Mm, Ma'am,
Yes.
on one
Okay.
hand, it is correct, ma'am, because that should terminate on the root, but I'm not getting how I should apply this point in these breakaway branches.
Can you see the material?
Yes, ma'am.
So this is basically the breakaway direction, right? Not the angles along which the root branches are approaching zero or tending towards infinity as k tends to infinity, right? So this is one root branch, complex root branch. This is the second complex root branch originated from this two open loop, complex open loop poles, right? So far, is this clear?
Yes, ma'am.
Yes, ma'am.
Now, these two root branches are meeting at this point, which is basically the break-in point to be very precise, right? This is the break-in point. So this is the direction in which this root branch, I am considering one root branch at a time. So this root branch is approaching this particular break-in point, or generally speaking breakaway point in this particular direction. Take a very close point on this root branch. So this, look at this direction, and this root branch is breaking away from this particular point and forming a real root branch which is moving in this particular direction, or this particular direction, whatever. So this is a straight line, this is another straight line, hence the angle is 90 degree. Two root branches are approaching each other, so breakaway direction will be plus minus 180 degree by r, in this case plus minus 180 degree by 2.
Yes,
Similarly, this root branch is approaching this break-in point. This is the point. This is the direction in which the root branch is approaching this particular point. And after meeting with this root branch, it's breaking away in this particular direction. So I can draw a tangent like this, and this is a straight line along the negative real axis. Hence, the angle will be given by 90 degree, not 180 degree.
Okay,
Now
so
is
got
it
it, ma'am.
clear? Now is it clear? This is the tangent. This is the direction in which the root branch is leaving the breakaway point. So the angle is 90 degree. Similarly, let's go back to this. Here also, this is the direction in which the root branch is approaching this complex breakaway point. And this is the direction in which this root branch is leaving. This root branch is leaving this complex breakaway point. Hence, the angle is obviously 90 degree. Have you understood? Now, is it clear?
Yes, ma'am. Yes.
Is it clear to everyone?
yes, ma'am.
So, should I close this file?
Yeah,
So,
sure,
that
ma'am.
is applicable for this
Yes,
breakaway point also. Okay. Now, stability in frequency domain. That is our last topic. We'll study Nyquist stability criterion. We'll study a stability criterion which is a frequency domain based stability criterion. So in this chapter, another very important and useful technique, which is Nyquist stability criterion, will be discussed, which relates, and this particular stability criterion, frequency domain based stability criterion, actually relates the location of the roots of the characteristic equation to the open loop frequency response of a system. And we know that the stability of a linear time invariant system is dependent on the location of the roots of the characteristic equation on the S plane, right? If all the roots are lying in the left half of the S plane, then the system will be absolutely stable. And if the if at least one root is lying in the right half of the S plane, while rest of the roots are lying in the left half of the S plane, the system will be unstable. And we have discussed all these things in detail. So this particular stability criterion, this is very important. It's a graphical technique, it's a visual tool, and it relates the location of the roots of the characteristic equation with the open loop frequency response of a system. So unlike the root locus technique, the computation of closed loop poles is not necessary in this case, and stability study can be carried out graphically from the open loop frequency response. Now the next line is equally important. Therefore, experimentally determined open loop frequency response can be used directly for the study of stability when the feedback path is closed. An open loop system means it doesn't have any feedback path. So from the open loop frequency response, which has been carried out experimentally, and we know how to find the open loop frequency response with the help of a simple experiment that we have already studied, that we have seen while we have discussed identification of linear system using frequency response test, right? So very easily, experimentally, and we have seen that the open loop transfer function was determined from that particular test. So using a very simple, implying a very simple experiment, we can find out the open loop frequency response. And from the open loop frequency response, we can ascertain the absolute stability of the system as well as relative stability of the system. Am I clear?
Yes, sir.
So the Nyquist stability criterion is based on a theorem of complex variable first derived by Cauchy. It's commonly known as principle of argument. So before we discuss Nyquist stability criterion, first we'll have to understand what is basically that particular theorem which is known by principle of argument. So this is basically the prerequisite or mathematical preliminaries. Let's assume a function QS. Let's assume a function QS. So from this, it's clear that Q is a function of S, where S is a complex variable given by sigma plus j omega. Now for the time being, please do remember that this QS is not the characteristic equation associated with a system. QS is any function. We could have written this as some AS or something like that. So in this book, they have preferred this sign, but now for the time being, we should keep in mind that QS is not the characteristic equation, any general expression which is basically a function of S. So this QS, also we assume that the QS is known in the factored form, and it's denoted by a numerator polynomial ns by ds, and where denominator polynomial, and the numerator polynomial is known or expressed in this factored form, as well as the denominator polynomial is expressed in factored form. So the numerator polynomial is given by s minus alpha 1, s minus alpha 2, s minus alpha m, whereas the denominator polynomial is product of all this factors, linear factors, which are s minus beta 1, s minus beta 2, s minus beta n. And s is basically a complex variable given by sigma plus j omega. Now, it's apparent that since s is a complex variable, a complex quantity, hence this qs, which is basically the function of s, will also be complex, isn't it? Hello?
Yes, ma'am.
So qs will be complex. So this qs can be represented as this equal to some u plus jv, right? S is given by sigma plus j omega, and since q is a function of s, hence it is qs will also be, if you evaluate qs at a particular point on the on this s plane, so that particular value of qs for that particular value of s, say equal to s0, will also be complex and can be denoted as, in general, as u plus jv. So QS can be denoted by U plus JV, right? So this S sigma plus j omega will give us a plane which is known as S plane, and the axes are labeled as sigma and j omega. Sigma is the real axis, and j omega, that is the imaginary axis. Now, since QS can be in general denoted by U plus JV, hence we can say that we are getting a new plane which can be denoted as QS plane. QS plane, and its axis will be labeled as U and V. U is the real axis and V will be the imaginary axis. Am I clear? Is it clear? So from the
Sure.
S, so from the S plane, with the help of this function given by s minus alpha 1, s minus alpha 2 divided by s minus beta 1, s minus beta 2, so a point on the S plane will be mapped onto a point on the QS plane. And the mapping function is this particular function, the expression of QS. So if we put a value s equal to s0, that means we are locating, identifying a point on the s plane, and for that particular value of s0, if alpha 1s are known and beta 1s are known, then we'll be able to find out qs0, and that particular point can be mapped on the qs plane. Hence, this is the mapping function. Have you understood?
Yes, ma'am.
Now, a particular value of A0 can be mapped or can be plotted on the QS plane given this function if a particular condition is satisfied. That means at that particular value s equal to s0, QS has to be analytic. If QS is not analytic at that particular point, s is equal to s0, then will not get the value of this function QS, or won't be, not the value, actually we won't be able to find out QS. Am I clear? Hello, is it clear?
Ma'am, what do you mean by ma'am analytical?
Analytic, you know what is meant by analytic. Analytic means a point where the function exists and its higher derivative exists.
Okay, ma'am.
Right? So at a point where the function or its higher derivatives don't exist, then that particular point is called a singular point. You have studied all these things.
Yes, yes.
Just try to recall. Try to recall. You know what is meant by singular point, isn't it?
Yes.
So unless is at S0 is equal to S0, QS is analytic, we won't be able to compute this QS for that particular value. And
Yes.
hence we won't be able to map that particular point on the QS plane. But at each and every point on the S plane where QS is analytic, we'll get a corresponding point which can be mapped onto the QS plane. Now, so far is this clear? If you don't understand principle of argument, you won't be able to understand Nyquist stability criteria, and you'll not be able to apply the same, right? So try to understand principle of argument clearly. If you have any doubt, please feel free to ask, okay? And please interact. So far, is this clear?
Yes, ma'am.
Yes, ma'am.
Now, suppose on the S plane, this is our S plane. We are quite familiar with this. And this is our QS plane, right? Denoted by U and JV. This is the QS plane. Now, on the S plane, let's take a closed contour. Closed contour means the starting point of this contour and the terminating point of the contour will be same. Now we are taking a close contour on the S plane, and we're assuming that given a QS, the contour doesn't pass through any singular point of that QS. Again, I repeat, we are taking a close contour on the S plane such that the contour doesn't pass through any singular point for a given QS. QS has to be given. The expression for QS has to be given. In this case, we have seen that this is QS. Okay. Now, let's start traversing this contour on the S plane in this direction. This is the arrow, as you can see. So we are moving along this contour in the clockwise direction. The contour is being traversed in clockwise direction. Okay. Suppose we are starting, as it's leveled as S1. So suppose we are starting from S1 and we are traversing the contour in the clockwise direction, and we are terminating at this point again, right? Now this is one convention. So in control system, in control engineering, we follow this particular convention that while we traverse the contour in this clockwise direction, right? And in the process, we start identifying the region which is lying to the right of this contour. Look, I'm traversing the contour in this direction, and this is the region which is lying to the right of this contour. And while I'm traversing in this particular direction, Just try to follow this contour in this particular direction, and we'll find that this is the region which is lying to the right of this contour. And while I'm traversing in this part of the contour, then clearly we can identify that this is the region. The shaded region is lying to the right of this contour. Do you agree? Yes or no?
Yes, ma'am.
So is it absolutely clear? So we are traversing this contour, close contour on the S plane, which we have chosen arbitrarily, but one condition has to be satisfied, that all the points on this contour, at all the points on this contour, the function QS will have to be analytic. Or in other words, the contour will not pass through any singular point for the given QS. And we are traversing this contour in the clockwise direction. In this direction means clockwise direction, and in the process we are shading the region or identifying the region which is lying to the right of this contour. Okay, so in this case, this region, this shaded region, this region will be said to be enclosed by this contour. Will said to be enclosed by this contour. And these regions which are lying to the left of the contour while traversing in this particular manner will said to be not enclosed by this contour. Is it clear? Now, in control system engineering, we follow this particular convention. The mathematicians generally follow a different convention, and the convention is something like this. We'll traverse this contour in the anti-clockwise direction. We'll traverse this contour in the anti-clockwise direction, and in the process, we'll try to identify the region lying to the left of this contour. You see, we are getting the same region. And the region which is lying to the left of the contour will be said to be enclosed by the contour. So we can use any of these two conventions, but being control system engineers, in this particular class, I'll follow this particular convention. That means we shall traverse a closed contour in the clockwise direction, and we shall try to identify the region lying to the right of the contour, and hence that particular region will be said to be enclosed by this contour. Clear?
Yes, ma'am.
Now, since this contour is not passing through any singular point of the QS, given QS, hence, look, for this S1, we'll get some QS1 which can be plotted, which can be mapped. This S1 point can be mapped on the QS plane as a point which is given by QS1. Similarly, this point S2, since this is not a singular point, hence for S2 we'll get some QS2, and that particular QS2 can be mapped on the QS plane. S3, for that we can map QS3, and we can proceed in this particular manner, and finally again, since the terminating point is S1, so we'll get QS1. Hence, for this closed contour that we have chosen arbitrarily on the S-plane, and which is not passing through any singular point for that given QS, on the QS plane also will get a closed contour. Have you understood what I'm saying?
Yes, ma'am.
So it's clear that for this arbitrarily chosen closed contour on the S plane which doesn't pass through any singular point for the given QS, on the QS plane, again, you'll get a closed contour. For the time being, just ignore this arrow direction. So you will get a closed contour. Now, we are not really concerned about the shape of the contour, shape of the closed contour that we are getting on the QS plane corresponding to the closed contour that we have chosen on the S plane. We are not interested about the actual shape of the contour. Instead, we are interested about the fact that whether the closed contour that we are getting on the QS plane, whether that particular contour encloses the origin of the QS plane or not. Number one. This is the origin of the QS plane, right? So we are interested about the fact that whether the closed contour on the QS plane encloses or encircles. The concept of enclosure or encirclement is same as that we have discussed in this particular case. So whether that particular the origin of the QS plane is being enclosed by the QS plane contour or not. And if the origin of the QS plane contour is being encircled by the QS plane contour, the QS plane contour is often denoted by tau Q. Tau subscript Q. So often we denote any contour by the symbol tau. So whether tau Q encircles the origin of the QS plane or not, if it encloses the origin of the QS plane, then how many times does this tau Q, that means the QS plane contour, encloses the origin of the QS plane? Okay. And third point of concern is in which direction the QS plane contour encloses the origin. Now, if I take this particular direction, if I assume this particular direction, then you see that this contour on the QS plane, yes, it does encloses the origin of the QS plane, as well as this QS plane contour actually encircles the origin of the QS plane once, only once, right? And it encloses the origin of the QS plane once in the counterclockwise direction, isn't it?
Yes, ma'am.
So applying principle of argument, we'll have to find out this fact. So the QS plane coordinates are denoted by U and V. The previous equation indicates that for every point S in the S plane at which QS is analytic, I have explained what is meant by analytic. We can find a corresponding point QS in the QS plane. Alternatively, it can be stated that the function QS maps the points on the S plane to the onto the QS plane. Since any number of points in the S plane can be mapped into QS plane, it follows that for a contour, closed contour in the S plane, which does not go through any singular point, there corresponds a closed contour in the QS plane. The closed is not written over here. It's very important. We are considering a closed contour in the QS plane as shown in this particular figure. The region to the right of a closed contour is considered to be enclosed by the contour when the contour is traversed in the clockwise direction. The other convention already I have mentioned. You can use any of these two conventions But I would prefer this particular convention, and just be sure that you don't mix these two conventions. Thus, the shaded area in this figure, or this shaded area, is said to be enclosed by this closed contour chosen in the S-plane. After explaining again, I am reading out these lines just to ensure that you understand this principle of argument clearly. So already we have discussed that we are not interested in the exact shape of the QS plane contour. For the time being, I don't want to mention Nyquist criterion, right? So only we have a closed contour in the QS in the S plane, and we have a closed contour on the QS plane, and we are not interested in the exact shape of the QS plane. An important fact that concerns us is the encirclement of the origin by the QS plane. Now, whether the QS plane, the origin of the QS plane will be encircled by the QS plane contour or not, for that, let's investigate the following cases. Now, first of all, let's assume that 1, 0 of QS is being enclosed by this S-plane contour. Now, from this expression, it's clear that alpha 1, alpha 2, alpha n, these are the zeros of QS, and beta 1, beta 2, beta n, these are the poles of QS. QS is any arbitrary function of S, not the characteristic equation, but any function expressed in this form will have poles and zeros associated with it. At alpha 1, alpha 2, etc., the value of QS will be 0, hence alpha 1, alpha 2, alpha m. All these are the zeros of QS. And at beta 1, beta 2, beta n, the value of QS will be infinite, and hence beta 1, beta 2, beta n, these are the poles of QS. Is it clear?
Yes, ma'am.
So let's assume that one zero of QS, say alpha 1 is being enclosed by all the poles and zeros of QS can be located on this S plane, and we assume that 1, 0 is being enclosed by this S plane contour that we have chosen, and all the the rest of the poles and zeros of QS are lying outside this enclosed region, somewhere over here, right? Only one single zero of QS is being enclosed by this S-plane contour. So consider an S-plane contour which encloses only one of the zeros of QS, say is equal to alpha 1, while all the poles and remaining zeros are distributed in the S-plane outside the contour. Now we have already discussed that QS is a complex quantity, hence QS can be expressed as magnitude of QS and angle of QS. U plus JV, that means we'll have a magnitude. If we express that in polar form, then we'll get the magnitude and a phase angle of QS. Now the magnitude is given by mod S minus alpha 1 into mod S minus alpha 2 into mod S minus alpha m divided by mod S minus beta 1 into mod S minus beta 2, so and so forth. That means these are the phasor lengths. S minus alpha 1 is the phasor, S minus alpha 2 is the second phasor. So these are the phasor lengths divided by this phasor length, product of this phasor lengths. Okay. Now we are not really bothered about this particular equation as this equation will actually give us the length of the phasor. Length of which phasor? QS phasor. That means the phasor that we are getting on the QS plane. This is one QS phasor, isn't it? This is one QS phasor.
Yes, ma'am.
So that particular equation which we discuss right now, so that equation will give us the phasor length, and hence that particular equation will actually give us the, considering also we'll have to consider the second equation as well, but that will give us the exact shape of the contour. But instead, as I said, we are really interested about the encirclement of the origin by the QS phasor. Now, the phase angle of the QS phasor is given by this, the angle of QS phasor is given by, since these are the zeros and hence their angle contributions will be positive, and the net angle contribution by all the zeros, to get the net angle contribution by all the zeros, will have to add the individual angle contributions by the zeros. Hence, the angle of QS will be angle S minus alpha 1 plus angle of this particular phasor, which is S minus alpha 2 plus dot 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 S minus alpha m, minus, since the poles are in the denominator, hence the angle contribution by the poles will be negative, that we know. So it will be minus angle S minus beta 1 minus angle S minus beta 2, and so on and so forth. Please look at this equation and try to find out whether you have understood this particular equation clearly or not. This is simple. This is a very simple phasor algebra. Is this equation clear?
Yes, ma'am.
Okay, so what we have assumed that the closed contour that we have chosen on the S plane does encloses 1, 0 of QS, which is alpha 1, right? Now, let's take a point on this contour, as we'll traverse this contour through this point lying on this particular contour in the clockwise direction. So if this be a point on the contour that we have chosen on the S plane, then we can construct this phasor. So this is S minus alpha 1, this one is S minus alpha 2, accordingly we'll get S minus alpha 3, so on and so forth. Just we have shown in this particular figure 2 zeros of QS has been shown, and this 3 poles have been shown, right? So this is the phasor which is S minus beta 1, this is the phasor which is S minus beta 2, and this is the phasor which is S minus beta 3. Is it clear? The phasor construction is clear?
Yes, ma'am.
Now, look very carefully. As I move along this contour in the clockwise direction, this particular phasor moves like this. So it will move like this. Am I clear? How the phasor is rotating along the contour?
Yes, ma'am.
Is it clear to everyone?
Yes, ma'am.
So this
Yes.
phasor is rotating like this. Hence, this phasor, as we start traversing along this contour from this point and we complete the traversal and we come again this 2 point, this phasor, the phase angle contribution of this phasor will change by angle which is 360 degree.
Yes, ma'am.
Clear? Now, as we are traversing the contour in the clockwise direction, hence net change in phase angle of this phasor will be equal to minus 2 pi.
Yes, ma'am.
Whereas, just consider this particular phasor. What is the difference between this and this? This point is being enclosed by this contour, whereas this point is not enclosed by this contour. So as we'll move around this close contour, you see this phasor will rotate like this. Am I clear? Have you understood?
Yes, ma'am.
So the net angle, net change in angle by this phasor will be equal to 0.
Yes, ma'am. 0.
Yes. And similarly, the net change in angle of this phasor will be 0.
Yes, ma'am.
So that is valid for all these poles and zeros which are lying, which are not being enclosed by this close contour. Only one zero is enclosed by this contour, and hence the net change in angle of this QS phasor, that is delta QS, will be equal to minus 2 pi. Minus 2 pi for this particular phasor, and delta of this will be 0, delta of this will be 0, delta of this will be 0. Now, so since net change in the phase angle of this QS phasor is equal to minus 2 pi, is equal to minus 2 pi, hence on the QS plane, since it's a closed contour, so we know that on the QS plane we are going to get a closed contour. So this is the QS phasor. This is the QS phasor on the QS plane. And since delta QS is equal to minus 2 pi, hence this QS phasor will rotate like this. We are not interested about the exact shape of the QS contour, but it's clear since delta QS is equal to minus 2 pi, hence the QS phasor will rotate like this, and in the process it will enclose the origin of the QS plane once in the clockwise direction, as delta QS is minus 2 pi. Have you understood this?
Sir, can you explain this once more?
Yes.
Only this part.
Your voice is not clear. Please repeat.
Ma'am, minus 2 pi part, can you repeat once more?
Minus 2 pi. So the 1 0 of QS is enclosed by this S-plane contour. It is clear?
Yes.
Now this is the phasor
Yes.
S minus alpha 1.
Yes, ma'am.
Just a minute. এটাকে ফুল স্ক্রিন করব কি করে গো? তোমরা কি ফুল স্ক্রিনে দেখতে পাচ্ছ? Am I visible?
Yes, ma'am.
Ma'am,
Yes,
after
ma'am.
Yes, ma'am.
ফুল স্ক্রিনে দেখতে পাচ্ছ?
Yes,
Yes.
ma'am. Yes, ma'am.
Can you see the pen?
yes, ma'am.
Yes, ma'am.
So the S minus alpha 1, that particular phasor, this is the phasor. So while I am traversing along the S-plane contour, you see this phasor will rotate like this along the contour. So what is the change in angle? 360 degrees, isn't it?
Yes, ma'am.
I'm
Yes.
starting from this point, I'm rotating like this, I'm coming to this particular point. So what is the change in angle? The change in angle, that is equal to 360 degree or 2 pi, right?
Yes, ma'am.
Now since I'm traversing in the clockwise direction, we know that if we move along the clockwise direction, then we'll get a negative angle. So the net change in angle will be minus 2 pi.
Yes, ma'am.
Now is it
Yes,
clear?
Yes, ma'am.
Now the other phases, that means the the phases which we have constructed considering the poles and zeros of QS lying outside the enclosed region, just look at this, the tip of the pen. Okay. Those phasor, while traversing along the S-plane contour, those phasor will move like this. And finally, the phasor will come to the initial position. So the net change in angle will be 0.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Is it absolutely clear?
Yes, ma'am.
Hence, for this particular phasor, since this 0 of QS is being enclosed by this S-plane contour, hence the net change in angle will be equal to minus 2 pi. Is that clear now?
Yes, ma'am.
So since the net change in angle is minus 2 pi, delta QS will be equal to delta S minus alpha 1, and all these terms will be 0. So since the QS phasor is rotating, delta QS means QS phasor is delta QS equal to delta angle QS equal to minus 2 pi, means the QS phasor on the QS plane is rotating by an angle which is equal to 2 pi and in a clockwise sense. Is it clear?
Yes, ma'am.
So this is one QS phasor. This is one QS phasor. I'm just joining a point, any arbitrary point on the QS plane to the origin. So I'll get a QS phasor. Yes or no? Yes or no? Hello? Hello?
Yes, ma'am.
So since net changing angle is minus 2 pi, first of all, let's first consider that the net changing angle is 2 pi. So this QS phasor will move like this. That means since the net changing angle is equal to 2 pi, hence the QS phasor will encircle the origin of the QS plane. And since the angle is associated with a negative sign, minus 2 pi, that means this QS phasor will rotate on the QS plane in a clockwise direction, and in the process it will encircle the origin of the QS plane once.
Yes, ma'am.
Now, is it clear to everyone?
Yes,
Yes,
ma'am.
ma'am.
So now let's assume that the S-plane contour now encloses two zeros of QS, say alpha 1 and alpha 2, and all other, the rest of the poles and zeros of QS are not being enclosed by this chosen S-plane contour. And the conditions remaining same, that this S-plane contour is a closed contour and doesn't pass through any singular point for the given QS. I'm repeating these things several times. So, and we are traversing the QS plane, S plane contour in the clockwise direction. So now we are considering that two zeros are being enclosed. Two zeros are being enclosed. Hence, so what is valid for alpha 1, one single zero, that will be valid for alpha 2 as well. So this will be the phasor, and this phasor again will start rotating like this as I have shown. So this phasor, the net changing angle of this phasor will again be minus 2 pi. Hence, the net changing angle when the two zeros are being enclosed by the S-plane contour, then delta QS, delta angle QS will be delta S minus alpha 1 plus delta angle S minus alpha 2, and the rest of the terms will be 0. So this will contribute an angle which is equal to minus 2 pi, and this will again contribute an angle which is equal to minus 2 pi. So delta angle QS now in this case will be minus 4 pi. Is it clear?
Yes, ma'am.
So now the QS phasor will encircle the origin twice in the clockwise direction. One encirclement because of the enclosure of this first zero, and the second encirclement of the origin by this QS plane contour because of the enclosure of the second zero by the S plane contour. And both encirclements will be in the clockwise direction. Is it clear?
Yes, ma'am.
So now we can apply the same concept, and instead of 0, now let's assume that the S-plane contour now encloses, for the time being, let's assume that the S-plane contour encloses one pole of the QS. One pole of the QS, right? So what will happen? In this case, if we assume that this is not a 0, but instead it's a pole, so this phasor will rotate like this. While we'll traverse this S-plane contour, the phasor will rotate in the same manner. Clear? So net change in angle will be equal to 360 degree, that is 2 pi. And since we are traversing this contour in the clockwise direction, and hence the net change in angle will be minus 2 pi. Right? But you see, from this expression, it's clear that the poles are lying in the denominator. Hence, the angle contribution of the poles will be negative. By default, the angle contributions of the poles are negative. So minus of minus 2 pi, suppose beta 1 is being enclosed by the S-plane contour. So minus of minus 2 pi, this one will be 0, net change in angle of this will be 0. So now we'll get delta angle QS, which is equal to minus of minus 2 pi, that is plus 2 pi. Have you understood this?
Yes.
Yes, ma'am.
So when a pole will be enclosed, then the QS phasor on the QS plane will encircle the origin of the QS plane once in the counterclockwise direction, in the opposite direction, because now the net change in angle of QS is plus 2 pi. Similarly, if two poles are enclosed, then the encirclement will be, the number of encirclement will be 2 and the encirclement will be in the counterclockwise direction. So is it clear? So far is this clear?
Yes, ma'am.
Yes, ma'am.
So now let's assume that P number of poles of QS, and Z number of zeros of QS are being enclosed by the S-plane contour. Again, I'm repeating, P number of poles of QS and Z number of zeros of QS are being enclosed by the S-plane contour. So then the QS plane contour tau Q, the QS plane contour tau Q will encircle the origin of the QS plane n number of times, capital N number of times, in the counterclockwise direction, and the number of encirclement n will be equal to P minus Z. If there are P poles and Z zeros of QS enclosed by the S-plane contour, then the corresponding QS plane contour must encircle the origin Z times in the clockwise direction as we have seen, and P times in the counterclockwise direction as we have seen, resulting in a net encirclement of the origin which is equal to P minus Z times in the counterclockwise direction. Is it clear? Take your time. Should I have to repeat?
ম্যাম পি টাইম তো অ্যান্টি ক্লকওয়াইজ করবে আর জেড টাইম ক্লকওয়াইজ করবে, তাহলে পি
Right. Anti-clockwise মানে counterclockwise.
হ্যাঁ
P
তাহলে
times in the counterclockwise and Z times, it's somewhere, yeah, Z times in the clockwise direction. So net encirclement of the origin in the counterclockwise direction will be P minus Z.
ও আচ্ছা, ঠিক আছে হ্যাঁ ম্যাম।
And that is equal to N. N is the number of encirclement of the origin of the QS plane by QS phasor in counterclockwise direction. So N is equal to P minus Z. Now is it clear?
Yes, ma'am.
So here they have considered one case, 1, 0 and 3 poles. So for the 3 poles, for these 3 poles, we'll get plus 2 pi, plus 2 pi, plus 2 pi. That means 3 encirclement of the origin in the counterclockwise direction, and for the single 0, which is being enclosed by the S-plane contour, there will be 1 clockwise encirclement of the QS plane's origin, right? So net counterclockwise encirclement of the QS plane origin will be 3 minus 1 times, that means 2 times, twice in the counterclockwise direction. And hence the encirclement can be shown in this, like this. Okay. So 1 counterclockwise rotation followed by the second counterclockwise rotation. And this is the origin. And hence we can see that this origin being, the origin of the QS plane is being enclosed once and then twice. Have you understood this?
Yes, ma'am.
So this relation, that means this relation between the enclosure of poles and zeros of QS by the S-plane contour and the encirclement of the origin by the QS plane contour is commonly known as principle of argument. And from our discussion, it is clear that if the S-plane contour that we have chosen doesn't enclose any pole or zero of the QS, given QS, right, then the QS plane contour will not encircle, will get a close contour on the QS plane, but the contour will not enclose the origin of the QS plane. Net change in angle, if we get back to this equation, since not a zero, not a pole, not a single zero, not a single pole is being enclosed by the S-plane contour, hence change in angle of QS will be 0, and hence the QS phasor, this QS phasor will move like this, and it will create a close contour, but the contour will not encircle the origin at all. Have you understood?
Yes, ma'am.
So now we'll apply this principle of argument for ascertaining the stability of a system, right? And that particular stability criterion is known as Nyquist stability criterion. So this QS is indeed the characteristic equation of a given system. So this is the characteristic equation, and it's clear that it's a characteristic equation as it's given by 1 plus GSHS is equal to 0. And GSHS is the open loop transfer function, And again, I'm repeating that this open loop transfer function can easily be determined by employing frequency response test. And this open loop transfer function, if we use frequency response test, then this open loop transfer function will come out to be in a factored form, right? So GSHS, suppose the GSHS is K into S plus Z1, S plus Z2 into S plus Zm divided by S plus P1 plus S plus P2 plus S plus Pn, where n is less than equal to n. So this is my open loop transfer function, and K is the gain. Now we know what is the significance of gain K, as we have studied route stability criterion as well as root locus technique. So from this equation, it's clear that minus zi's are the open loop zeros of the system, since this is the open loop transfer function, and minus pj's are the open loop poles of the system. Do you agree?
Yes, ma'am.
So again, I am repeating, since GSHS is the open loop transfer function, hence minus zi's are the open loop zeros of the system, and minus pj's are the open loop poles of the system. Now, for determining the stability of the system, that means the stability means actually we want to find out the stability of the closed loop system. That means when we close the feedback path, then whether the system is stable or not, that is of concern. Okay, so we want to find out the closed loop stability of the system, and the merit of Nyquist stability criterion is that from the open loop transfer function, or in other words, from the open loop frequency response, we can determine the closed loop stability of the system. Closed loop stability of the system. So this is QS, which is equal to 1 plus GSHS equal to 0. So from this open loop transfer function, let's now try to obtain the characteristic equation of the system. QS is equal to 1 plus GSHS, that means 1 plus K S plus Z1, S plus Z2, S plus Zm by S plus P1, S plus P2 plus S plus Pn, right? So now this can be written as, in the denominator we'll have this S plus P1, S plus P2, S plus Pn, and now in the numerator we'll get the first, this, if I call this to be the first term will be 1 into all this, so S plus P1 into S plus P2 into S plus Pn plus K into S plus Z1, S plus Z2 plus S plus into S plus Zn. Clear?
Yes, ma'am.
So if I expand, if I multiply these factors, then it's obvious that the denominator polynomial will be of the order n. What about the numerator polynomial? What will be the order of the numerator polynomial? If I multiply all this, and then after that, if I combining this, if I again factorize the numerator polynomial, then what will be the order of the numerator polynomial?
Nth order.
Nth order, right? So now we can write the numerator polynomial in a factored form as S plus some Z1 dashed plus into, not plus, sorry, into S plus some Z2 dashed dot S plus Zn dashed. This Z1, Z2, Zn will not be equal to Z1, Z2, sorry, Z1 dashed, Z2 dashed, Zn dashed will not be equal to Z1, Z2, Zn. Now,
Yes, ma'am.
right? So this is my characteristic polynomial. So if I equate this to 0, then this z dashed i's will give us the roots of the characteristic equation, isn't it? Yes or no? So all this zi or all this minus z1 dashed minus z2 dashed minus zn dashed are the n number of roots of the characteristic equation for an nth order system.
Yes, ma'am.
Yes, ma'am.
And the poles poles of the characteristic equations are located as at minus p1 minus p2 minus pm, right? So that was my open loop transfer function. This part is my open loop transfer function. So what we find that the open loop poles are same as the poles of the characteristic equation. Just compare this two. The open loop poles are located at minus pjs and the poles of qs are also located at minus pjs. Is that clear?
Yes, ma'am.
So the locations of the poles of the characteristic equation is known to us since we know the open loop transfer function of the system. So where those pjs are located, or minus pjs are located, that can be determined by simply inspecting the open loop transfer function of the system.
Yes, ma'am.
Yes,
Right?
ma'am.
Okay. So now for the stability of the system, what is required? It's required that all the roots of the characteristic equation, that means all this zi dashed should lie in the left half of this plane, that we know. Right? Again, I can extend this that for a stability of the system, some of the poles of the characteristic equation, some of the poles of the characteristic equation, that means some of the poles of the open loop transfer function or some of the open loop poles may lie in the right half of this plane, but for the system to be stable, all the roots of the characteristic equation should lie in the left half of the SP. Do you agree?
Yes, ma'am.
So now, if I can find out, I'm coming to Nyquist stability criteria. Now, if I can find out the number of roots of the characteristic equation which are lying in the right half of the SP, then I'll be able to comment on the stability of the closed loop system. Again, I am repeating. If I can find out by some means, by applying principles of argument, since we have discussed principle of argument, so by applying that particular theorem, if we can find out the number of roots of the characteristic equation lying in the right half of this plane, then I'll be able to comment on the stability of the system. If the number of the roots of the characteristic equation lying in the right half of the S-plane is 0, then obviously the closed loop system will be stable. And if some of the roots of the characteristic equation are lying in the right half of the S-plane, then obviously the system will not be stable. It will be an unstable system.
Yes, ma'am.
Right? So now we'll try to find out whether we can determine the number of roots of the characteristic equation lying in the right half of the S-plane. So already we have seen that the zeros of QS or the roots of QS are located at minus Zi dashed. And these are the roots of the characteristic equation, and the poles of QS lying at minus Pj's are same as the open loop poles of the system. Now also we have discussed that for the system to be stable, the roots of the characteristic equation and hence the zeros of QS must lie in the left half of the S-plane. So it's important to note that even if some of the open loop poles lie in the right half of the S-plane, so that means if some of the open loop poles lie in the right half of the S-plane, that means the open loop system will be unstable. If some of the open loop poles lie in the right half of the S-plane, that implies that the open loop system itself is unstable. But after closing this feedback path, if we find that all the roots of the characteristic equation lying in the left half of the S-plane, that means that with the help of this feedback path, an open loop system can be made to be stable. An unstable open loop system can be made stable. Have you understood? So it's important to note that even if some of the open loop poles lie in the right half of the S-plane, all the zeros of QS, that is the closed loop poles, may lie in the left half of the S-plane, meaning thereby that an open loop unstable system may lead to a closed loop stable operation. Is that clear? Is it clear? Should I proceed?
Yes.
Now, in order to investigate the presence of any zero of QS in the right half of the S-plane, that is our strategy. That is going to be our strategy. Or that was Nyquist strategy actually. So in order to investigate the presence of any root of QS in the right half of the S-plane, let us choose a contour on the S-plane which will completely enclose the entire right half of the S-plane. So what is the objective? We are trying to find out the presence, whether any root of the characteristic equation is in the right half of the S-plane or not. Now to find out that, remember that particular equation, n is equal to z minus p, right? So to find out that, what we are doing, we are choosing a close contour in the close contour on the S plane, which will completely enclose the entire right half of the S plane. So such a contour will consist of one infinite straight line and another infinite or another semicircular arc having infinite radius. So along the straight line is we'll look at it with the imaginary axis, and along the straight line we know that S will be equal to j omega, and omega is varying from minus infinity to plus infinity. Here, and for the semicircular arc, we can represent the value of S on this particular arc as S equal to r e to the power j theta. This is j theta. R e to the power j theta, where limit r tends to infinity. So this semicircular arc will have an infinite radius. Okay, and r e to the power j theta, r e to the power j theta. So we will move along this close contour in the clockwise direction. So we'll start moving along this direction and we'll start moving in this particular direction. So that is our clockwise direction. We'll traverse this close contour in the clockwise direction, and hence the theta, the value of theta will vary from plus pi by 2 to 0 to minus pi by 2. This is plus pi by 2. The value of theta at this point is plus pi by 2. Then the value of theta is changing. At this point, the value of theta is 0. And at this point, as we are moving along the clockwise direction, the value of theta is minus pi by 2. So along this semicircular arc, the radius of the semicircular arc will tend towards infinity, and the theta value will vary from plus pi by 2 to 0 to minus pi by 2. So if we choose such a contour, such a close contour on the S plane, then it's clear that this particular contour is actually enclosing the entire right half of the S plane. Am I clear? Have you understood this?
Yes, ma'am.
Is it absolutely clear?
Yes, ma'am.
So such a contour on the S plane, such a close contour on the S plane, which will completely enclose the entire right half of the S plane, is called a Nyquist contour. This is called a Nyquist contour. So for this Nyquist contour, if this QS is given, that means if the open loop transfer function is given, that means QS is known, right? We are determining the closed loop stability of the system from the open loop frequency response. That means this open loop transfer function is known. That means this QS is known. So for this Nyquist contour on the S plane, we'll get a closed loop contour on the QS plane. Now this QS is the characteristic equation. And this is the mapping function. This is the mapping function. So we'll get a closed contour on the QS plane, yes or no?
Ma'am, can you please repeat it again after plotting the Nyquist contour?
So this is my Nyquist contour. I've
Yes, ma'am.
chosen this particular contour, nothing to do with the QS. Now, since the open loop transfer function is known, as we have already discussed that Nyquist, with the help of Nyquist stability criterion, from the open loop frequency response, we can determine the closed loop uh, stability of the system, right? That means this open loop transfer function is known.
Yes, ma'am.
So that means the characteristic equation QS is known.
Yes, ma'am.
So this is now my QS. This is my QS. These are the zeros of QS. These are the poles of QS, right? So just think of this case. Principle of argument. Principle of argument, right? We assume that QS is known, hence QS is given. So for this Nyquist contour, on the S-plane, since QS is known, hence this QS will now be the mapping function, as we have discussed, is the mapping function. Hence, a point on the Nyquist contour on the S-plane can be mapped on the corresponding QS plane. If we assume that the Nyquist contour that we have chosen is not passing through any singular point of this QS.
Yes, ma'am.
Now, have you understood? So, corresponding to this S-plane contour, which is now our Nyquist contour, corresponding to this S-plane closed contour, will get a corresponding QS contour as we have discussed.
Yes, ma'am.
Okay. So the Nyquist contour so defined encloses all the right half S-plane zeros and poles of QS, if any. So this Nyquist contour, which is enclosing the entire right half of the S-plane, will certainly enclose the right half zeros and poles of this QS, if any.
Yes, ma'am.
Do you get my point? If some pages are there in the right half of the S-plane, and if some roots of the characteristic equation, that means some zi dashed are there in the right half of the S-plane, then those zi dashed and those pages will certainly be enclosed by this Nyquist contour. Am I clear?
Yes, ma'am.
So now if we assume that z number of zeros of the characteristic equation and p number of poles of the characteristic equation are in the right half of the S-plane, then the corresponding QS plane contour will encircle the origin of the QS plane capital N number of times in counterclockwise direction, and its value will be equal to P minus Z, where P is the number of poles of QS lying in the right half of the S-plane, and Z is the number of zeros of QS lying in the right half of the S-plane, and thus these are being enclosed by this Nyquist contour. Have you understood this?
Yes, ma'am.
Right?
Yes, ma'am.
So, yes, n is the number of encirclement of the QS plane, origin of the QS plane by the QS plane contour, and this in the counterclockwise direction, and this value of n will be equal to p minus z, where p is the number of the poles of the characteristic equation lying in the right half of this plane, remember, and z is the number of the roots of the characteristic equation lying in the right half of this plane. Okay, now for a closed loop system to be stable, we know that no roots of the characteristic equation should lie in the right half of this plane. That means the value of z should always be 0 for stability, which gives us a condition which is equal to n is equal to p. This is my condition, n is equal to p. Right? And in the commonly occurring cases where the open loop system itself is stable, the open loop system is stable, that means all the PJs are lying in the left half of the S plane, and hence number of open loop poles lying in the right half of the S plane is 0. So in commonly occurring cases when the open loop system is stable, then the value of P will be equal to 0. Hence, Z should be equal to 0. The open loop system is stable, hence P is equal to 0. Therefore, for a system to be stable, N should be equal to 0. Number of encirclement of the origin of the QS plane by the QS plane contour corresponding to the Nyquist contour taken on the S plane should be 0.
Ma'am, can you tell me why we have taken P as 0?
Why I have taken P as 0? That is, if the open loop system itself is stable. This is my open loop transfer function, this one.
Yes, ma'am. I got it.
This is my open loop transfer function. So if the open loop system is stable, right? So these are the poles of the open loop system, and this is the same as the poles of the QS, as we have already said, right? So that means if the open loop system itself is stable, that means all the poles of QS will lie in the left half of the S plane.
Yes, ma'am.
So that means, that implies that number of poles of QS which will lie in the right half of the S plane will be 0, since the open loop system is stable.
Yes, ma'am.
Hence, we are taking the value of P to be 0 when the open loop system is stable. Now, we know for the system to be stable, Z should be equal to 0. If the open loop system is stable, then P is equal to 0, right? So, for a system to be stable, N should be 0. Let me read out. In order for the system to be stable, there should be no zeros of QS, that is 1 plus GSHs, in the right half of the S plane. That is, Z should be equal to 0. This condition is satisfied if N is equal to P. As for the system to be stable, Z should be equal to 0. Now the next part is, so that is, this equation can be explained as, for a closed loop system to be stable, the number of counterclockwise encirclements of the origin of the QS plane by the contour tau q, that means QS plane contour, should be equal to the number of right half S-plane poles of QS, which are the poles of the open loop transfer function GSHs. As GSHs is generally known in the factored form, so number of poles of GSHs lying in the right half of the S-plane can be determined by simply inspecting the open loop transfer function, which is given. So if the transfer function is something like this, k into the numerator part is I'm not discussing the numerator part. Suppose in the denominator we have three poles like s plus 1, s plus 2 and s minus 3. So simply by inspecting this open loop transfer function, we can find out that yes, one open loop pole is there which is in the right half of the S-plane. S minus 3. S plus 1, that means the first pole is lying, open loop pole is lying at S equal to minus 1. S plus 2, that means the second open loop pole is lying at S equal to minus 2. And since the third one is S minus 3, that means that particular open loop pole is lying in the right half of the S-plane. Hence, the number of open loop poles lying in the right half of the S-plane is equal to 1. So how many open loop poles are actually lying in the right half of the S-plane? That can be determined by looking at this particular open loop transfer function. So as GSHS is generally known in the factored form, the number of such poles P is easily ascertained by inspection. And the second part is, in the special case, this is generally the case in the most single loop practical systems of P is equal to 0. That means the open loop system is stable. The closed loop system will be stable if the number of encirclement of the origin of the QS plane by the QS plane contour corresponding to the Nyquist contour in the counterclockwise direction is equal to 0. Have you understood this?
Yes.
Is it clear? Now, GSHS can be written as 1 plus GSHS minus 1. This is my QS. I can write GSHS as QS minus 1, where QS is equal to 1 plus GS. Yes or no?
Yes, ma'am.
Now, what was the problem with this? We can determine the closed loop stability of the system using this technique, but in this case, you see, we'll have to find out the characteristic equation, QS, right? But we claim that the Nyquist stability criterion is a simpler one where from the knowledge of the open loop system itself, we can determine the closed loop stability of the system. That means we don't have to compute the characteristic equation. So that is why we are discussing this part, and we'll establish, yes, the stability can be ascertained from the knowledge of the open loop transfer function itself. We don't need to know the closed loop transfer function. That means the characteristic equation. So GSHS is equal to 1 plus GSHS minus 1. So this is my QS plane, and suppose this is the QS plane contour tau q, corresponding to some Nyquist corresponding to the Nyquist contour that we have drawn on the S plane. So this is my QS plane contour. So this is my QS vector, right, which is 1 plus GH vector. Do you agree? The bold one is the QS plane contour. This is my QS plane. QS plane contour, right? This is my QS plane contour. Hence, if I join a point on this contour to the origin, then I'll get the QS phasor, which is nothing but 1 plus GH phasor. Yes or no?
Yes, ma'am.
Now, on this QS plane, this we identify a point which is -1 plus J0. -1 plus J0. So the point will lie somewhere on this negative real axis. And this point is known as the critical point. Critical point, right? -1 plus J0. So this is a phasor having a length which is equal to 1. Yes or no?
Yes, ma'am.
So 1 plus GH, 1 plus GH -1 is equal to, this is the resultant phasor, and which is nothing but GH. As 1 plus GH -1 is equal to GH. So this is my 1 plus GH phasor, this is my -1 phasor. So if I draw the resultant phasor is nothing but the GH phasor.
Yes, ma'am.
Okay, so my purpose is served. Now, instead of this origin, instead of this particular point, now if I consider this to be the critical point, right, then we can define another plane which is GH plane. Which is GH plane, and generally we label the axis as real and imaginary, right? So a GH plane whose origin has been shifted at this particular point. Have you understood what I'm saying? Now the origin, we have given simply a translation of this axis now, right? -1, by -1. Yes or no?
Yes, ma'am.
So the plane that we get is said to be the GH plane, right? But we don't place the imaginary axis at this particular point. We draw the imaginary axis at this particular point, and this we call the critical point. And now, instead of counting, so on the GH plane, we'll get a contour tau GH, whose shape will be identical to the shape of the QS plane contour. Because 1 plus GH -1, simply -1. Hence the shape of this is my GH plane contour, tau GH. So this contour will have the same shape as the QS plane contour, right? So we'll draw this contour and we'll label the plane as GH plane, but will not draw the imaginary axis at this point. Instead, we'll call this point to be the critical point. And now, instead of counting the encirclement of the origin of the QS plane by the QS plane contour, we'll count the encirclement of the critical point, which is -1 J0, by this GH plane contour in the counterclockwise direction. Is it clear?
Yes.
So now we can state, so from GH, from the knowledge of GH, we can find out the number of encirclement corresponding to the Nyquist contour on the S-plane, and hence we can determine the stability of the system or closed loop stability of the system. That is the merit of the Nyquist stability criterion. If the contour tau GH of the open loop, this is our Nyquist stability criterion, if the contour tau GH of the open loop transfer function GSHS corresponding to the Nyquist contour in the S-plane encircles the point -1 plus J0 in the counterclockwise direction as many times as the number of right-half S-plane poles of GSHs, that means this first condition, number of encirclement is equal to the number of poles of GSHs in the right-half of the S-plane, right? Now this time the number of encirclement will be the number of encirclement of the critical point by the GH plane contour. Again, I am repeating, if the contour tau GH of the open loop transfer function GSHS corresponding to the Nyquist contour in the S plane encircles the point -1 plus J0 in the counterclockwise direction as many times as the number of right-half S-plane poles of GSHs, the closed loop system is stable. That means from this equation it's clear that Z will be 0. The number of roots of the characteristic equation lying in the right half of the S-plane will be 0, and hence the system will be stable. In the commonly occurring case of the open loop stable system, the closed loop system is stable if the contour tau GH of GSHs does not encircle -1 plus J0, this critical point, that is the net encirclement is 0, this condition. P is equal to 0. Since Z has to be 0, hence N should be 0. Right? So, if we can construct the GH plane contour, then by inspecting the GH plane contour, we can determine the number of encirclement of the critical point by this GH plane contour. That means by looking, if we can construct the GH plane contour, then looking at that particular contour, we can find out the number of encirclement of the critical point by tau GH. P we can determine from the open loop transfer function itself, right? So putting the values of A and P in this equation, we can find out the value of Z, that means number of roots of the characteristic equation lying in the right half of the S-plane. So if Z comes out to be 0, then the system is stable. The closed loop system is stable. And if Z is not equal to 0, then the closed loop system will not be stable. Now, this GH contour on the GH plane is called the Nyquist plot. The S-plane contour, which encloses the entire right half of the S-plane, is called Nyquist contour, and tau GH or GH plane contour is called the Nyquist plot. Have you understood this? Yes or no?
Yes, ma'am.
So I'll request you to go through this uh, topics, that means principle of argument and Nyquist stability criteria, up to this once, because tomorrow we'll have the last class, I guess, on Nyquist stability criterion. And if you can't understand, if you have any doubt about the principle of argument or this Nyquist stability criterion, then you will not be able to apply Nyquist stability criterion for judging or ascertaining the stability of the system, which we are going to discuss in tomorrow's class, right? So since the topics are a bit involved, so please at least to go through this material at least once. So for the time being, do you have any query? Any doubt?
No, ma'am, but we need a example
Yeah,
so that we can check the stability with the use of Nyquist
that
law.
will do in tomorrow's class. That's why I'm telling you to go through this topics, that is principle of argument and Nyquist stability criterion. Otherwise, while solving the problem, you'll get confused. You might get confused. Please go through this.
Ma'am,
Hello?
ম্যাম বলছি নাইকুইস্ট প্লটে ওই অ্যারোটা ম্যাম ক্লকওয়াইজে তো দেওয়া রয়েছে।
Hmm?
এই যে প্লটটা, এই প্লটটায় অ্যারোটা তো ক্লকওয়াইজ দেওয়া রয়েছে, তাই আমি
This plot is an arbitrary plot. So the arrow direction will depend upon this equation. P number of encirclement, as I said, P number of encirclement in counterclockwise direction, Z number of encirclement in clockwise direction, and hence N is the number of encirclement in the counterclockwise direction. And that will be clear, the arrow direction will be clear when we'll solve a couple of problems.
ওকে ম্যাম।
So should I?
Is it easier to find the Nyquist plot of a practical system?
Yes.
Because we can get an understanding of the stability by looking at the transfer function, but sometimes it is difficult to find the
No, you cannot determine the stability by looking at the transfer function. It's not that simple. If it's an higher order system, and if the transfer function is expressed in polynomial form, ratio of two polynomials, then how will you be able to find out the stability of the system? By solving the characteristic equation. It's a very tedious and time consuming task for a 7th order system, or even for a 4th order system. If you try to solve the characteristic equation which is of the order of 4, it's not going to be so simple. So that's why we are studying all the stability criterion. Had it been the case that we can ascertain the stability of a system simply by looking at the transfer function of the system, then Proust stability criterion, Nyquist stability criterion, or Hurwitz stability criterion, those criterions were not required at all. You get my point?
Yes.
Okay, so do you have any further question? Or should I close this material? Can I end the session?
Yes.
yes, ma'am.
Okay. So tomorrow we'll be having a class sharp from 6:30. I'll send you the link.